I have an answer for your question. You wanted to know with the Sallen key filter, what happens if the gain gets bigger than 3? And it's actually really interesting. And I'm sort of annoyed that I didn't know the answer right off the top of my head, because as soon as I figured it out, I was like, oh, of course. Right, so what does the, in the Sallen key filter, what does the gain term kind of do for you? It sets the damping coefficient, right? So in the Sallen key filter, remember that the RC, that's not the part of the gain, the R and the C gives you the omega naught, and then the gain basically sets the damping coefficient. So if your gain is low, then you basically have a gain a zeta that's like the most damped you could have, and then which is 1. And then if your gain is 3, there's like basically no damping. So what happens is, if you think about your pole 0 diagram, if you have two poles that are right here, that's basically very, very heavily damped. So that's zeta. This is like zeta pretty close to 1, which means a gain that's pretty close to 0. Then you start increasing your gain. So let's say you keep omega naught the same. So you start increasing your gain. So I want you to imagine like a circle with radius of omega naught, right? Omega naught radius. So as you start to increase your gain, these poles start to travel along the circle, okay, until they get right up to the edge. Now, when they're right up to the edge, this means gain is 3, which means that zeta is pretty close to 0. Okay, and now that's like, if you think about the transfer function, now it's getting like really, really peaky here. If your gain exceeds 3, which you're certainly welcome to do, now your poles cross over into the right half plane. And then you have an unstable system. And that's what happens. Well, what do I mean by an unstable system? A stable system means that if you put in a bounded input, you get a bounded output. So like, for example, if you put in a step, that's a bounded input, right? It doesn't go up to infinity. If you put in a step, that means that your output may wiggle and do some stuff, but eventually it'll like settle out to some sort of finite value. If you build me this circuit and put in a step, eventually your output will blow up to infinity. So, instead of getting something that ripples down like this, you'll get something that ripples off to infinity. I don't know quite how it gets there, but the point is it'll blow up. So there you go, unstable system. Okay, right, what to do? So I'm going to heroically attempt to finish Chapter 9 today. And the way I'm going to do that is basically by not covering all of Chapter 9, mostly because I've decided that everybody here has eyeballs and can probably read. So what I'd like to do is to kind of hit what I think are the highlights of Chapter 9 and kind of work some sample problems. And then I'm going to leave you to read the textbook, and then hopefully the problems that I've assigned will help kind of focus your attention a little bit on the parts that just kind of need some rote practice. And then I think, depending how today goes, we may do a little bit of cleanup on Friday, but probably we'll just move on to Chapter 10. Okay? So here's the topics I kind of want to cover for today. One is the concept of RMS. Has everybody heard of RMS, root mean square? Is that kind of at least vaguely familiar? Yeah. For a cosine. Right, but not, for other signals, maybe not 0.707, but yes. Okay. So there's RMS. I want to talk briefly about power factor. And then I want to talk about complex power. And I'm going to do all of this in 40 minutes, because I got to leave you 10 minutes for your quiz. So let's start briefly with this. So the name of the game that we've been playing is, we have a power supply, and we're driving an impedance, and we've been trying to calculate like what's going on power-wise in the impedance. So what we decided is that if your voltage can be expressed as a phasor. Oh yeah, theta v. And if your current can be expressed as a phasor, then the power in the load can be expressed as 1/2 Vm Im, and then it was cosine theta v minus theta I. Now, do you remember like the whole bit with the resistors and the capacitors and whatnot? If your load has some resistors and some capacitors in there, where's the power getting burned? All of the power is getting burned in the resistors. What's happening in the capacitors? Back and forth, right? It's like it's taking power, but then it's sloshing it back. So it's not, on average, it's not really consuming any power. So one of the things we're going to look at is complex power. Complex power is basically like regular power, but it includes an imaginary term. And it turns out that all that power the average power that was zeroing out in the capacitor, turns out we can think of it as complex power, and we can actually account for it in the complex power calculation. So we'll look at that in a minute. Yes, sir?
Is that average power?
Yeah, this is the average power. Right. This is power in the load averaged over one period. Okay? So there's a couple things we're going to look at. So for the RMS, so RMS is basically a shorthand for figuring out like an effective current or an effective power. So if we, for example, like if you were to look at a resistor, right, and put a cosine across it, we would know that the power in that cosine would go according to this equation, right? It would be 1/2, Vm, Im, cosine, whatever the angle is. But it turns out, actually, well, for cosine, what would be the, well, sorry, let me rephrase this. So if we just had a resistor, what's the power through the resistor? It's just IV, is it not? All right. So, what's that? Which is the same as I squared R. But if our signal is if the power through there or the current through there is a cosine, then we can remember we talked about the average power. Let me just write this real quick and then I'll explain what I'm talking about. So if you're so basically if the current going through this resistor is a cosine or whatever, some sort of periodic signal, then you can calculate the average power by doing I squared R as long as you use the average power formula, right, where you integrate it and then divide by the period. So it turns out this is kind of a pain in the butt to do because nobody likes to do these integrals over and over again. So what we're going to do is we're going to introduce this concept that says, look, I don't want to keep doing this. So instead what I'm going to do is I'm going to calculate what is the effective current going through that resistor, right? So in other words, if I've got this resistor and the current through it looks like that, I can definitely do I squared R, integrate over one period and divide by the period to calculate the effective power. But a much faster way to do it would be to say, look, this is sort of equivalent to this constant, I effective. And if I do I squared R for this effective current, then that will give me the same power as I would have gotten if I'd gone through all the trouble of integrating. Okay, so it's basically like a one-time shortcut. So if you solve this, you wind up finding out that your effective current, or your effective voltage, if you're doing this with voltage, is, let me just again write this down because it's hard to talk and integrate at the same time. So if you've got a periodic signal, be it a current or voltage or whatever, if you square it average it over one period, and then take its square root, you get a constant, which is like the effective power of that, or like the effectiveness, basically, of that cosine. Yes, of that signal. Just, oh, t, one period. Integrated over one period. It doesn't matter. Just integrate it over one period. Like start at 0 and end at t. Or start at minus t over 2 and end at t over 2. It doesn't matter. Just integrate it over one period. That's what that shorthand means. Okay, so it's kind of a cool shorthand because what happens is that once you do that, you don't have to worry about like, oh, my signal's a cosine. I've got to deal with integrating it and so on. You just say, okay, it's you can basically just treat your cosine current or your cosine voltage as a constant. You just adjust it for the fact like sometimes if your current's a cosine, you're basically saying sometimes it's high, sometimes it's low. The effective current says if you average it over one period, you basically get this equivalent value. Okay? So look what you're doing here. You're taking the square root of the average of the square. Right? So it's the root of the mean of the square, and that's why we call it RMS. Now, you can find the effective RMS value for any periodic signal, right? And in fact, in the homework, I think I give you, some example where, like, let's say your signal looks like that. You can calculate its effective RMS value. Okay? So in other words, what's the constant that would give you this an equivalent power? But since most of the time, in this course especially, we're dealing with cosines, we can actually calculate the RMS value for a cosine. So suppose x of t equals let's say I of t. So let's say I is some cosine at some frequency. So if we were to apply the RMS formula, and again, they do this derivation in the book, and I have zero interest in copying out like 10 lines of calculus from the book for your note-taking pleasure. I'll refer you to the book for the actual derivation. But if I were to take the RMS value of a cosine, any takers on what I'm going to get for my result? Yeah?
0.707.
Yeah, it turns out that what you get is 0.707 IM. Okay, that's the effective, which is the same as root 2 over 2. That's the effective power of the signal. So basically what will happen is that a lot of times when it comes to power especially, we don't talk about like the peak voltage of a cosine. We talk about its RMS value. It's sort of like its effectiveness. Okay, so we talk about the power outlets. We talk about it's 120 volts RMS, right? It's not peak to peak. It's RMS, and that's essentially just giving you its effective power. Yes.
The cosine, what does it stand for a current or voltage?
Oh, it could be the same, right? I mean, if I gave you a voltage, it would be 0.707 times the voltage magnitude. So here's the advantage in doing this. I know it seems like a bit more drama than necessary, but I assure you that it's going to simplify a lot of our notation. Because originally we had said that when your power is cosine, or when your source is a cosine, we said that the power was 1/2 V magnitude I magnitude cosine theta V minus theta I. Okay, so it's not that this is wrong, it's just that it's kind of a drag because we have to remember like one formula for sinusoids and one formula for, like, we're really more used to seeing I squared R or I times V for power. So it turns out that if instead you derive this using RMS power, you can just write it as VRMS IRMS times the cosine term. So that's sort of the value of writing your power, your signals in terms of their RMS equivalent, is that you get back to an expression that makes a little bit, that's more consistent from one equation to the next, right? You never have to, like, if instead of a cosine, I were to give you a square wave input, okay? Well, instead of having to rederive this, remember this was specific for cosines. Instead of having to rederive this for, if your input was a square wave, you'd say no problem. Just give me the RMS voltage and the RMS current, and this formula still applies. Okay, so basically this will be your power equation, regardless of what the shape of the input signal is. All you got to do is just express your voltage and your current as an RMS value, as opposed to having to recalculate a power equation for a cosine or a square wave or a triangle or whatever it is you have. Just give me the RMS values. It's voltage times current, the end. So far, so good? All right, it gets worse. Okay, so having said that, the book makes an interesting point. It sort of takes your power and it expresses it into two pieces. So this it calls apparent power. And this it calls the power factor. Okay? And the power factor, so you can basically think of it like the apparent power is sort of the most power you can push. And then the power factor is sort of like a multiplier that can be anywhere from 0 to 1 that will tell you kind of like how effective you are at driving your power into your load. And the book actually does a pretty cool example that I wanted to go through. Where am I? So I'm going to do example 910, if I can find it. Because it does a pretty nice job of illustrating the power factor concept. And then we'll talk about power. We'll talk about complex power. So we are looking at example 910. So in example 910, they're basically talking about an industrial load that consumes 88 kilowatts, and then they give you the power factor. So they're giving you the load, the power at the load is 88 kilowatts at a power factor of 0.707, I think they called it lagging, and I'll talk about what that means in a second. And then they tell you that the line is 480 volts RMS. So the line equals 480 volts RMS. So this is like real high power stuff. This is like basically what it looks like coming from the power company. And what they want to know is, and then they're telling you that this has the voltage at the load, and then they're telling you that the line that they're going to push this through, like the actual wire, has a pretty low resistance of 0.8 of an ohm. So the question then becomes, how much power does the power company have to supply in order to deliver this much power to the people who are using it? So this might be like some manufacturing facility or something, and they need to get like a pretty big thing of power from the power company. So the question is, how much power does the power company have to supply? How much power does the power company have to supply in order to deliver this to the customer?
The line is Arno.
Yeah, no, the line is basically, I'll show you what the line is. Hold on. So here you've got your power company. The power company is going to push power through the cables that go from the power company to the manufacturing facility. So this is your 0.8 of an ohm. And then, we're not exactly sure what's going on in the factory, but we know that the factory is consuming 88 kilowatts at 0.707 lag. And we know that this voltage is 480 volts RMS. 480 volts RMS. So the question is, how much power did the power company have to deliver? Yes, sir? 0. Let me make sure I get it right. Yeah, it's 0.08. That's a pretty low resistance wire, huh? So I want to know, what's my supply power? So what's a reasonable strategy for figuring this out? Find the current. I mean, I already know how much power is being burned in the load. I basically just have to figure out how much power is being lost on the line, and I add them together, and that'll be how much power is being generated by the power company, right? I mean, the power company has to deliver the load power plus whatever the losses are on the wire. What do the losses look like on the wire? Heat. It's wasted, right? It's just lost. Power company had to create it. Nobody could use it. That's bad, right? It just costs everybody money. So let's start by figuring out what is the RMS current that is working here. So how can I calculate the RMS current? Yep. We know that the average power has to, at the load, has to equal the RMS voltage at the load times the RMS current at the load times the power factor. Okay, where the power factor was remember we said power factor was the cosine. And essentially when you express power factor, you're basically saying, like, I don't really care what the phase of the voltage and the phase of the current is. I'm just going to pre-calculate it, and they just come up with this power factor. Like, if you were to know theta V and theta I and take their difference and take their cosine, it would come out to 0.707. Okay? So I can work this problem backwards to figure out my current. So if I work this problem backwards, I find out that my current is going to be power at the load divided by VRMS times the power factor. Okay, so let's sub in some numbers. So 88 kilowatts divided by 480 volts divided by 0.707. Woo, that's a big number. Somebody verify. 259.3. Is that K? Is that amps? RMS. Is that a lot of current? That's a lot of current. That will wake the dead, maybe literally. Okay, good. What do you get? Nope. No. Recalculate. 88K. You got 259? The 259s are winning. Let me see. I'll try it on my end. Where's my calculator? You got it? 88 E3 and I'm going to divide that by 480 And then I'm going to divide it again by 0.707. Yep, I'm getting 129.6. No. Did I do it wrong? 259. Okay, good. I don't know what I did. All right. Now, so now that I know the RMS current going through this resistor, can I calculate the losses in that resistor? All right, how do I calculate the losses in the resistor? How do I calculate the power in the resistor? I effective squared R. Or sorry, not I effective, I RMS. You see why we use RMS? Because when you use RMS, you can just say I squared R. That's just how power works, right? I squared R in a resistor. If we didn't do that, then we'd have to figure out, we'd have to figure out the magnitude of the voltage, the magnitude of the current, and then do that whole like 1/2 VI times the cosine. It's a nightmare. But if you do it like this, it's just a simple calculation. Just a nice, clean I squared R. Okay, so let's do I squared R. What do we got? 5.38 kilowatts. So this is really interesting, right? So the power company basically has to supply 88 so at the source, you have to supply 88 kilowatts plus the 5 and change. So what is that, 93.4 kilowatts? Okay, so what happened to that 5 kilowatts? Gone! That's a lot of power, right? 5 kilowatts to keep the lights on for a little while. Yes, sir?
That's the power across the resistor, the second one?
Right, that's the power that's lost across the resistor. That's just being dissipated as heat in the line. So here's the really interesting thing. Suppose now at the facility, at the manufacturing facility, they start messing with their power factor a little bit. They're going to consume the same amount of power. Okay, they're going to consume the same amount of power, but now they're going to change their power factor to 0.9. Are they using the same amount of power?
No.
Yeah, they're still using 88 kilowatts, right? But what they're doing is they're just changing. Remember, power factor is the cosine of the voltage. Sorry, is the cosine of the difference between the voltage angle and the current angle. So if current and voltage are aligned, right? If I were to draw current and voltage like this, what's the angle between them? 0. And the cosine of that 0 is 1, and therefore the power factor is 1. So when they're aligned, your power factor is 1. Okay? When they're out of phase, when like your voltage has 1 cosine and your current is out of phase, then your power factor gets smaller. What if they're 90 degrees out of phase? If they're 90 degrees out of phase, your voltage and your current, so you have cosine of 90 is 0. So if they're 90 degrees out of phase, then you have a power factor of 0. What does it mean? What kind of load do you have when voltage and current are lined up? Just a second. What's the kind of load you have when voltage and current are perfectly aligned? Purely resistive. And what about when they're 90 degrees out of phase? Purely capacitative or purely inductive. Okay? And if it's somewhere in between, then it's like a sum of resistance and capacitances. Yes, sir?
Is this for voltage and current? Like, but I was saying, yeah, like 2 voltages out of phase, would it like certain points to double or?
But we're talking about power, which is voltage times current. So that's why we're just looking at those two expressions. So we're looking to see how closely they are in phase. Okay, so we just did an example where, and we'll come back to this in a second. So we just looked at an example where power factor was 0.707. Now we're going to up the power factor to 0.9. Keeping in mind that the power company isn't using any less power. They're just changing the phase relationship between the voltage and the current that they're drawing. But they're still using the same power. So let's redo this calculation, changing power factor to 0.9. Well, hold on, I'm hearing numbers. So what does this change to if I go to if I change the power factor? 203.7 amps RMS. And then what's the power that's lost in the line? 3.32 kilowatts. Isn't that cool? Look at what just happened. The power company is, the utility, the people, the users are still using the same amount of power. Okay? They're still receiving the same amount of power, but now, just by changing the phasiness, okay, of their load, it's actually causing less power to be burned in the resistor, in the line. It's more efficient, so everybody saves money, right? Either they're going to pay less for their power, the power company's going to waste less. I mean, it's whatever, it's a win. So let's just think through this intuitively for a second, because it's kind of important. If I've increased my power factor from 0.7 to 0.9, have I made my load more or less resistive? Remember, we said power factor 1 means voltage and current are aligned. And voltage and current are aligned when your load is purely resistive. Okay? So if your power factor has increased, has gotten closer to 1, they've gone out of their way to make their power more resistive. Why would that mean less line loss? Yes, exactly. Think about it, if your load is more capacitative, what do capacitors do with power? Whoosh. They use it and then they throw it back. What's going to happen with all that current that's being sloshed back? It's going to get lost. It's going to get lost in the line. So what you want to do is kind of design your load to have a power factor as close to 1 as possible, to be as resistive as possible. Because to the extent that it's capacitative, remember capacitors charge and then discharge. And when they discharge, where's all that current going to go? Right back through that resistor, which means line losses. So that's really cool, right? We could actually waste less power just by modifying, not how much power the utility uses, but just the phasiness of it. Yes?
Are there applications where that it's desirable to have more loss, like secondary output or something like that? Or is it not?
I'd have to think about that. I don't know.
It's just
There's always, I mean, I'm sure you could think of something. There might be. I don't know offhand, but there might be. That's a good question. So what could the end users be doing to increase their power factor? There's another example of this in the book that you should probably go through because you have a homework assignment that is basically just like the example in the book. Plug in what? Not so much, almost. Basically what you could do is you could stick a capacitor across like in parallel with your load. All right, and if you got the size of the capacitor right, you could basically change the phasiness of your load, and thereby get your power factor closer to 1. So there's a calculator in the calculation in the book where they basically figure out exactly how big of a capacitor you need to increase your power factor. Okay, but essentially that's what you're doing is you're figuring out how much current, how much power is being thrown back onto the line, and you're putting a cap there to say, hey, instead of throwing that current back onto the line, throw it into me. I don't care. I'm just sitting here, right? I like taking extra power. So it basically, you size this thing so that when there's power to be thrown off by the load, instead of being thrown off into the line, you throw it back into this capacitor. Okay, and thereby it's more efficient. You don't waste your power in the load, in the line. But I love this example. I always find it fascinating because in both cases, you're not really changing the amount of power that's getting used. You're just being more efficient about how you capture it. Right? To some extent, there's not much you can do about it. Right? To some extent, you've still got to get that 88 kilowatts through that resistor. Right? So you're still going to have some losses. You can't get that loss down to 0, but you can certainly minimize the damage. Questions? Okay, well, I like that example. Yeah, no? You're just stretching. Okay, good. Okay, no, we're good. Okay, so we're going to talk about, very briefly, complex power, and then we'll wheel out the quiz. By the way, you're heading to lab this week. We're going to start a final project. Elliot and I have been working on the final project. I think you're going to like it. We're going to be playing with sounds. You're actually going to take an output from your iPod and put it into a circuit and make lights come on. And I don't know, we got a whole bunch of cool stuff planned. So keep an eye out for that. Okay, so we're going to do one last thing, which is this concept of complex power. So if you're paying attention last week, you heard me say that power is only dissipated in resistors, and on average there's no power dissipated in capacitors. Did I not say that? Turns out that was sort of true. It wasn't a lie, but it wasn't as truthy as it could have been. So what we're going to do today is like fill in the gaps a little bit. So again, I'm skipping much of the derivation that's in the book, but we have this concept. Instead of P for power, we're going to talk about S. S is complex power. And S is going to be comprised of P, which is our friend real power, the thing that we've already looked at, plus JQ. So P is real power, and Q has a couple different names, but I like the term quadrature power. Okay, quadrature is basically a fancy engineering term for 90 degrees out of phase. It's literally what it means. Quadrature power means quadrature anything. Like you'll see quadrature when you go to I don't know, probably to see Dr. Szilagyi for one of his comm classes. Like, you talk about quadrature stuff a lot. Quadrature just means 90 degrees out of phase. So you have real power, then you have the complex, the quadrature power. So the way it works is power, real power, that's the exact same thing we've been looking at all along. V I times the cosine of the angle between them. Theta V minus theta I. You'll never guess what Q is equal to. V, I, and what's that? What's 90 degrees out of phase with the cosine? Sine, bring it home. Sine of theta V minus theta I. So, you remember when we did the example with the resistor and the capacitor? And we calculated how much power was being consumed in the resistor and how much power was being consumed in the capacitor. We found that all the power was consumed in the resistor, and on average, 0 power was being consumed in the capacitor. Turns out, we were only talking about real power. Okay? If you calculate the quadrature power, you get the opposite. You find that in a resistor, no quadrature power is being consumed. Okay? But you find that there is quadrature power being consumed in the capacitor. Sorry, did I get that backwards? I didn't get it backwards. I just said it stupidly. There's a difference. In a resistor, okay, so for a resistor, you have some power, you have real power, but you have no quadrature power. Right? All the power that goes through the resistor, voltage and current are, what's the voltage-current relationship in a resistor? Are they in phase or out of phase? They're perfectly in phase. So for a resistor, theta V and theta I are the same. You've got cosine of 0 is 1. So that's it. You have power. How much quadrature power do you have in a resistor if the voltage and the current are in phase? You have sine of 0, which is 0. So you have no quadrature power. Okay. What about in a capacitor? We've already done the power, right? We've already done the real power. Right? We've done that before and figured out that the real power is 0. What's the quadrature power of a capacitor? Is it positive, negative, or 0? How do you get negative? You're not wrong. I'm just saying, how'd you get negative? How could I know for sure? If you've got a capacitor, remember it's V equals IZ, where Z is minus J over omega C. So if your V has some phase angle, so in other words, this is going to be I times 1 over omega C angle minus 90 degrees. So let's see. So if your current has phase angle 0, what does your voltage have? Right? If your current has a phase angle of 0, and you multiply these together, what's your voltage phase angle going to be? Negative 90. Okay? So for a capacitor, you have sine of negative 90 minus 0. What's sine of negative 90? Minus 1. Minus 1 times whatever V RMS times I RMS is. So the point is, the quadrature power is negative. And for an inductor, the real power is 0, and the quadrature power is a positive for just the opposite reason. So you have this pretty elegant derivation, and again, the book goes into this in a decent amount more detail. I'm just trying to give you like the background you need to make sense of the examples in the book. But we can think about power is either a real power, which is the kind of power that's dissipated in a resistor, or we can think of quadrature power, which is the kind of power that's dissipated in an inductor or a capacitor. Okay? And the sign of the quadrature power just tells you whether you're talking about something that's more capacitative or something that's more inductive. Okay. Well, let's have a quiz.